Singapore is an aging population, with nearly 1 in 5 citizens expected to be a senior by 2030. With that comes many health issues. One common one, which you might have heard of, is cataracts. Hello, I'm Daniel, and I've been working on image-based cataract diagnosis as my final year project. Before delving into the diagnostic process, let's understand what cataracts are. Essentially, cataract is the clouding of the lens inside the eye, and it stands as the leading cause of visual impairment globally, affecting nearly 100 million people as of 2019, according to the World Health Organization. It is treatable, especially when diagnosed early, so the key challenge lies in diagnosis. Many cases go undetected due to the limited accessibility to screening methods, and that's where this project comes in. Currently, ophthalmologists rely on eye charts and expensive fundus cameras for diagnosis, making accessibility a challenge. The proposed handheld slit lamp camera with a machine learning model addresses this by being affordable, portable, and requiring less expertise to use. However, the proposed method poses several key challenges. Firstly, the quality of slit lamp images are much worse compared to fundus images. Secondly, the slit lamp images dataset used in this project is small and imbalanced in comparison to fundus datasets. And lastly, machine learning-based approaches typically create black box models which lack explainability. In order for new medical technologies to be approved, it must be possible to medically review. Therefore, the goals are to mitigate the poorer quality of the slit lamp images by introducing an image preprocessing pipeline and to complement the image-based model with patient metadata. Second, it is to overcome the small imbalanced dataset via image augmentation. And lastly, to provide model explainability by generating saliency maps. The proposed cataract diagnosis pipeline is made of two main parts, the image pipeline on the left and the modeling pipeline on the right. Slit lamp images first enter the image pipeline where they are preprocessed. Then, image augmentation is used to increase the size of the training set. Next, in the modeling pipeline, transfer learning is used. The weights of a ResNet 18 model trained on an ImageNet dataset are first loaded, then the model is fine-tuned with the slit lamp images and the patient metadata. Finally, the fine-tuned model is used to generate model predictions and the saliency maps. The dataset I am working with comes courtesy of Khoo Teck Puat and Tan Tock Seng Hospital. They provided a total of 187 slit lamp images with the corresponding visual acuity and contrast sensitivity data. This is relatively smaller than the ODIR 5K dataset, which consists of fundus images from 5,000 patients. The provided dataset is also quite imbalanced, with around 10% of the total images being healthy eyes. This can negatively impact machine learning performance, especially in predicting the healthy eyes class. To assess the effectiveness of complementing patient metadata, I trained two models, the proposed image plus metadata model, and then an image-only model to serve as the control. To assess the effectiveness of image augmentation, I created three dataset configurations: baseline with no augmentation, balance where healthy samples are generated to roughly match the number of cataract samples, and large where both healthy and cataract samples are generated to aid the model training. To validate the models, the mean accuracy, F1 score, sensitivity, and specificity are calculated across 20 independent loops, each with a randomized test set. An important point to note is that any patient chosen in the test set will be excluded from the train set to prevent data leakage. From the experiments, we can see that the more augmented images, the higher the mean accuracy. The image-only model improved from a mean accuracy of 0.74 in the baseline to 0.925 with the large augmented dataset. The same general trend can be seen for F1 score and specificity. This shows that the image augmentation is effective. Similar trends can be seen for the image plus metadata model. In fact, the best model was achieved with the highest mean accuracy of 0.96. This best image plus metadata model compares favorably with other studies as its mean accuracy is only 0.02 lower than the top performer, the Inception ResNet V2 model by Hassan et al. This small gap can be explained by the relatively lower quality of SLIM images and the smaller original dataset size. So overall, the proposed image plus metadata model performs satisfactorily. Okay, next. Now, let's take a look at the saliency maps. These were generated at each convolutional layer of the ResNet 18 architecture. We can observe that the conv1 and 2 focus on the finer details, while conv3 highlights the general regions used for diagnosis. Therefore, it is recommended to use conv3 for explaining cataract diagnosis. Then, to get a more summarized view of the saliency maps, I created an average saliency map for each convolutional layer across all data samples. We can see a similar pattern to the individual saliency maps, where conv1 and 2 are more detailed. Overall, the model focuses on features in the eye and near the illumination. Hence, this further validates the predictive power of the model. In conclusion, the image preprocessing, the complement of patient metadata, data augmentation, and saliency maps combine to give an accurate and robust cataract diagnosis using slit lamp images. Further development could be done to integrate the pipeline into handheld slit lamp camera for real-time saliency mapping and diagnosis assistance. Thank you.